The stars hold our greatest unanswered question. We are setting out on a galactic tour to 30 alien worlds, each a potential home for life beyond Earth. By the end, you will have a map to the most promising real estate in the cosmos for finding our cosmic neighbors. We will visit planets bathed in eternal twilight, worlds that might be global oceans, and super-Earths with skies unlike anything here. What does it feel like to look at the night sky now, knowing what might be out there? Our journey begins just 4.2 light-years away, a cosmic stone's throw from our own solar system. Orbiting the closest star to our Sun, Proxima Centauri, is a world that shattered our sense of neighborhood. Proxima Centauri b is a rocky planet with a mass about 1.2 times that of Earth, and it sits right in the star's habitable zone, that sweet spot where temperatures could allow liquid water to exist on its surface. For the first time, the dream of another Earth was not a distant fantasy but a specific address. The discovery in 2016 felt monumental, a revelation that potentially life-friendly worlds could be our immediate neighbors. Yet, this neighbor lives in a turbulent household. Proxima Centauri is a red dwarf star, smaller and cooler than our Sun, but notoriously temperamental. It unleashes violent stellar flares, eruptions of radiation and charged particles that could strip away a planet's atmosphere and bathe its surface in deadly levels of ultraviolet light. So the central mystery of Proxima Centauri b is one of survival. Could this world, so tantalizingly Earth-like in size and position, hold onto a protective atmosphere long enough for life to emerge and endure? Scientists are now focusing intensely on this question, using the most powerful telescopes to hunt for traces of an atmosphere. Detecting one would be a game-changer, suggesting the planet has a shield against its star's fury. This makes it a prime target, our first and most accessible laboratory for testing whether life can persist in such a challenging environment. The very fact that we can ask these detailed questions about a world in another star system marks how far we have come. Proxima Centauri b is not just a planet. It is a promise and a test, a beacon in our backyard urging us to look closer. But what if our solar system was not the only one with a family of worlds? Just 39 light-years away, we find a star system that redefines the word family. The star is TRAPPIST-1, another red dwarf, but one that holds a staggering secret. Orbiting it are not one or two, but 7 rocky planets, each roughly the size of Earth. It is a miniature solar system, a cosmic matryoshka doll of worlds huddled close to their dim sun. The journey from the outermost planet to its star would be shorter than the distance from our Sun to Mercury. And in this compact, bustling neighborhood, one world stands out as the most promising address for life we have ever found beyond our own solar system. That world is TRAPPIST-1e. It is the 4th planet from its star, a rocky world with a density and size almost identical to Earth's. Most crucially, it sits squarely in the middle of the star's habitable zone. The temperatures there are just right, in theory, for vast oceans of liquid water to exist on its surface. Think of it, a world with Earth's blueprint, orbiting in the perfect spot around its sun. But the conditions on its surface would be utterly alien. Like many planets around calm red dwarfs, TRAPPIST-1e is likely tidally locked. One side forever faces its star in permanent, blistering daylight. The opposite side is locked in eternal, freezing night. This sounds like a recipe for 2 extreme and lifeless hemispheres. Yet, between these 2 inhospitable realms, science suggests a narrow band of possibility could exist. Along the razor-thin line where day meets night, known as the Terminator line, conditions might be just temperate enough. Here, in a perpetual golden hour, you could have liquid water, stable temperatures, and an environment where life could potentially take hold. It is a world of stark contrasts, where the habitable zone is not a global condition, but a literal line you could walk across. The compact nature of the TRAPPIST-1 system offers an incredible opportunity. Because the planets orbit so close together and transit so frequently, we can study them in unprecedented detail. The James Webb Space Telescope is already turning its gaze toward these worlds, not to take pictures of surfaces, but to read their skies. By analyzing the starlight that filters through their atmospheres during a transit, Webb can hunt for the chemical fingerprints of water vapor, methane, carbon dioxide, and even potential biosignatures like oxygen. TRAPPIST-1e is not just a single candidate. It is the crown jewel of a system that represents our best chance to answer the question, are we alone? Finding an atmosphere there would be the next monumental leap in our search. The search for a twin of our own world leads us to a star over 1,000 light-years away. There, the Kepler Space Telescope found a planet that felt hauntingly familiar, a world named Kepler 452b. This is not a planet around a turbulent red dwarf, but one orbiting a star remarkably similar to our own Sun, a G2-type star. It completes an orbit in the habitable zone every 385 days, a year just 20 days longer than our own. For a moment, the data painted a picture of Earth 2.0. Yet the details reveal a more complex and fascinating story. Kepler 452b is not Earth's twin, but perhaps its older, bigger cousin. It is about 60% larger than our planet, placing it in a category we call a super-Earth. This extra size brings profound questions. Does it have a rocky surface like Earth? Or is it a mini Neptune, shrouded in a thick, gaseous envelope with crushing pressures? We do not yet know for certain, though many astronomers lean toward a rocky composition. The most compelling aspect of this world is not just its similarity, but its seniority. The Kepler 452 system is estimated to be around 6 billion years old, making it about 1.5 billion years older than our solar system. That is an almost unimaginable head start. If life did emerge on this super-Earth, it has had an extra 1.5 billion years to evolve, to complexify, to potentially become something extraordinary. What might life achieve with that much time? On our own planet, in just a few 100 million years, life exploded from single cells to the dazzling diversity we see today. An additional 1.5 billion years is a canvas for evolution to paint on a scale we can barely comprehend. The star it orbits is also aging, growing brighter as sun-like stars do in their later stages. This means the planet's habitable zone is slowly drifting outward, and Kepler 452b may be experiencing a warming climate over deep time. It presents a powerful thought experiment, a glimpse into a possible future for our own world, and a profound question. In a system older than our own, has life already navigated the challenges we may one day face, and perhaps reached heights of intelligence or civilization we have yet to achieve? Yet for all the promise of these distant cousins, the most compelling candidates are often the quiet ones. LHS 1140b is a super-Earth that has astronomers leaning forward with genuine excitement. Orbiting a small, quiet red dwarf star about 40 light-years away, this world represents a different kind of hope. It is not the closest, nor the most Earth-like in size, but it may be one of the most stable and observable laboratories for life we have ever found. The first clue to its significance is its density. Measurements tell us this planet is incredibly dense, far denser than Earth. The best explanation is that LHS 1140b is a rocky world with a colossal iron core, a planet built like a heavy, solid cannonball. This immense core suggests two thrilling possibilities. First, it likely means a robust, rocky surface where oceans and continents could form. Second, and more importantly, that density gives the planet a powerful gravitational grip. This strong gravity is a guardian for the most precious resource a world can have, an atmosphere. While a planet like Proxima Centauri b might struggle to hold onto its air against stellar flares, LHS 1140b has the sheer mass to potentially cling to a thick, protective atmospheric blanket for billions of years. This possibility is amplified by the serene nature of its sun. Unlike the violent tantrums of Proxima Centauri, the star LHS 1140 is remarkably calm for a red dwarf, with very low flare activity. It offers a stable, gentle light, a cosmic neighbor that does not constantly scream at its planetary children. This combination, a dense, rocky world with strong gravity orbiting a quiet star, creates a sanctuary where conditions could remain stable for eons, long enough for the delicate chemistry of life to begin. Furthermore, the geometry of this system is a gift to astronomers. The planet passes directly between its star and our telescopes on Earth, an event called a transit. Each transit is an opportunity. As starlight filters through the planet's hypothetical atmosphere, it carries chemical fingerprints, allowing instruments like the James Webb Space Telescope to potentially detect water vapor, carbon dioxide, or even signs of biological activity. LHS 1140b is not a flashy candidate, but a profoundly steady one. In the search for life, longevity and stability are everything, and this dense, quiet world may offer both in abundance. But what if the most Earth-like world we have found is not bathed in the light of a sun, but in an eternal, deep red dusk? Venture just 12 light-years away, to a star so faint it was not discovered until the year 2003. Teegarden's star is an ancient red dwarf, a dim ember in the cosmic dark. And orbiting this quiet, elderly star is a planet that holds a remarkable title. According to the Earth Similarity Index, a formula that compares a world's size, density, and temperature to our own, Teegarden star B is one of the most Earth-like exoplanets ever detected. Its minimal mass is just over 1 Earth mass, and it orbits snugly within its star's habitable zone. On paper, it is a near-perfect match, yet the reality of standing on its surface would be an experience of profound alien beauty. Because Teegarden's star is so incredibly dim, a planet must huddle extremely close to it to feel any warmth. Teegarden's star B completes a full year, one orbit, in only 4.9 Earth days. This proximity almost certainly means it is tidally locked. One hemisphere forever faces its dull crimson sun, the other stares eternally into the blackness of space. But here is where the conditions become fascinating. The star provides so little heat that even the permanent day side would not be scorched. Instead, the entire planet likely exists in a state of perpetual global twilight. The sky would be a deep, burnt orange, like the last moments of sunset stretched across an entire world. The sun, fixed unmoving in the heavens, would be a large, dark red disk, too dim to cast sharp shadows. Under this eerie, gentle glow, the possibility for liquid water hinges entirely on one critical factor: an atmosphere. If Teegarden's star B possesses a thick enough blanket of air, that atmosphere could act as a global heat distributor, circulating warmth from the day side to the night side. This could prevent the planet from freezing solid on one half and create temperate conditions across vast regions, perhaps even allowing for global oceans under that constant red sky. The calm nature of its ancient star is another point in its favor, offering a stable environment over billions of years. This world challenges our imagination, not with fire or ice, but with stillness and subtlety. It asks us to picture life not under a bright yellow sun, but in the soft, endless twilight of a deep red dawn. The dream of a water world is not science fiction, but a scientific possibility 1,200 light-years from here. In the constellation Lyra, the Kepler telescope discovered not one, but two such worlds orbiting the same star, Kepler 62. This star is smaller and cooler than our Sun, a quiet orange ember around which dance 5 known planets. Two of them, Kepler 62e and Kepler 62f, are super-Earths that forever changed how we picture the habitable zone. They showed us it was not a single line, but a broad, diverse neighborhood where vastly different kinds of worlds could each hold the potential for life. Kepler 62e is the inner of the pair, a world about 60% larger than Earth, It orbits closer to its dim star, completing a year in just 122 days. The warmth it receives suggests a global reality far beyond our own. Scientists modeling this planet find that the most likely scenario is a world without any land at all. Imagine a planet where the only horizon is an endless, gentle sea, stretching in every direction under a soft orange sun. The entire surface could be a single, planet-wide ocean, hundreds of miles deep, with pressures at the bottom so immense they create exotic forms of ice, not cold but hot and solid. In such an alien ocean, life would not cling to rocky shores, but would float or swim in a three-dimensional aquatic universe. The chemistry for life could thrive near hydrothermal vents on the ocean floor, or in sunlit upper layers if the atmosphere is clear. This is a world defined not by continents, but by currents, a global water cycle operating on a scale we can scarcely comprehend. Its sibling, Kepler-62f, is the colder, more distant counterpart. About 40% larger than Earth, it takes 267 days to orbit its star, placing it at the very outer edge, the cooler fringe of the habitable zone. Here, the sunlight is faint. If this world has a thin atmosphere, its surface could be a frozen, icy shell, more like Europa or Enceladus in our own solar system. But that is not the end of the story, it is the beginning of another. A thick atmosphere rich in greenhouse gases like carbon dioxide could act as a planetary blanket, trapping enough heat to maintain liquid water on the surface. Even without that, the possibility of a subsurface ocean remains powerfully alive. The internal heat from radioactive elements in the planet's core, or the gravitational squeezing from its star, could keep a vast liquid water ocean trapped beneath a thick crust of ice. Life on Kepler-62f would then exist in eternal darkness, hidden from the stars, thriving in a deep, pressurized abyss warmed from below. Together, these two worlds from the same stellar family revealed a critical truth. The habitable zone is not a precise recipe for Earth clones. It is a spectrum of possibilities. At the warmer inner edge, you can have steaming, global ocean worlds like Kepler-62e. At the colder outer edge, you can have icy shells guarding secret seas, like Kepler-62f might be. They proved that liquid water, the one ingredient we know is essential for life, can exist in profoundly different planetary environments. This discovery forced astronomers to broaden their search, to consider that a frozen, seemingly inert world might be hiding the most vibrant of secrets just beneath its surface. The Kepler-62 system gifted us with a pair of contrasting visions, two different answers to the same fundamental question of where life could make a home. 22 light-years away, a planet orbits in a sky filled with three suns. This is the world GJ667cc, a super-Earth that once topped the list of potentially habitable exoplanets. It belongs to a remarkable triple-star system, but it circles only one of them, a small, dim red dwarf named GJ667c. The planet itself is a heavyweight, over 4 times the mass of Earth, placing it firmly in the super-Earth category. Its orbit of 28 days puts it right in the center of its star's habitable zone, a prime location for liquid water. For years, this combination of factors made it a darling of the exoplanet community, a world that seemed to have all the right ingredients. Yet the very thing that makes its home so spectacular, the triple-star system, also introduces a layer of profound complexity. From the surface of this super-Earth, its parent red dwarf would hang in the sky as a large, dull red disk. But the two other, brighter stars in the system would also be visible, appearing as exceptionally brilliant stars, casting a significant amount of additional light onto the planet's surface. This is not the gentle, romantic glow of a distant star. This extra illumination from 2 additional suns would have a real and measurable impact on the planet's climate, potentially warming it further and creating a more dynamic, less predictable environment. The stability of its orbit and its climate over billions of years becomes a fascinating puzzle. Could the gravitational tugs from the other stars stir its orbit into chaos? Or has it found a stable, harmonious path, a cosmic dance that has persisted for eons? While newer discoveries have slightly tempered the initial excitement, GJ667cc remains a powerful symbol of the diversity of stellar environments that might host life, proving that a stable home can exist even in a crowded, multi-star neighborhood. Sharing the same dim red sun is its sibling, GJ667cf. This planet offers a completely different vision of habitability. It orbits farther out, taking 39 days to circle its star, placing it on the colder, outer fringe of the habitable zone. The sunlight here is feeble. If this world has a thin or non-existent atmosphere, its surface would be a global, deep freeze, a snowball world locked under miles of ice. But as we learned from Kepler 62f, cold does not mean dead. It often means hidden. The most compelling possibility for GJ667cf is that of a vast subsurface ocean. The internal heat from its rocky core, or the gravitational flexing from its star, could provide enough energy to keep a layer of liquid water trapped between a frozen surface shell and a solid seafloor. Life, if it exists here, would be cut off from the triple suns blazing in the sky above. It would thrive in perpetual darkness, in a pressurized aquatic realm, perhaps around hydrothermal vents on the ocean floor, drawing energy from the planet's own geology. This world forces us to expand our definition of a habitable environment. It is not about a pleasant, sun-drenched surface, but about the presence of liquid water and an energy source, no matter how deeply buried or isolated from the stars. Together, GJ667cc and F present two faces of the same system, one a warmer, potentially temperate super-Earth bathed in the light of three suns, the other a frozen enigma possibly guarding a secret sea. They remind us that in the search for life, we must look not just at the surface conditions, but at the total environment, from the complex gravitational ballet of multiple stars to the hidden, heated depths of an icy world. This search for hidden oceans leads us to a world that shattered expectations, forcing us to rewrite the rules of habitability entirely. 120 light-years away, in the constellation Leo, orbits a planet named K218b. For years, it was catalogued as a mini-Neptune, a world significantly larger than Earth but smaller than the ice giants in our own solar system. Conventional wisdom said such planets, swaddled in thick, hydrogen-rich atmospheres with crushing pressures, were gas-shrouded hellscapes, utterly inhospitable to life as we know it. Then the James Webb Space Telescope looked, and everything changed. The data revealed something astonishing. In the atmosphere of this distant world, Webb clearly detected the signatures of water vapor, carbon dioxide, and methane. This alone was a landmark discovery, the first time these key molecules had been confirmed together in the atmosphere of a planet in the habitable zone. But the real shock came with a tantalizing, unconfirmed hint. The data also suggested the possible presence of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is only produced by life, specifically by phytoplankton in our oceans. It is a potential biosignature, a chemical shout in the atmosphere that says something alive is here. This single, cautious signal from a world 120 light-years away sent a tremor through the scientific community. It forced a radical rethink of what a habitable planet could look like. K218b is not a rocky super-Earth like those we have visited before. It is a different class of world entirely, now theorized to be a Hycean planet. The name comes from hydrogen and ocean. Picture a planet with a rocky core, but instead of a thin atmosphere like Earth's, it is enveloped by a deep, dense atmosphere of hydrogen. Beneath this immense atmospheric blanket, the pressures and temperatures could allow for a truly alien environment, a planet-wide, superheated global ocean. This is not a gentle, Earth-like sea. The surface of this ocean would be blisteringly hot, perhaps hundreds of degrees, but kept liquid by the incredible pressure from the atmosphere above. In the eternal darkness of its lower depths, however, conditions could be far more temperate. The hydrogen-rich atmosphere might act as a giant insulator, trapping heat and creating a stable, watery environment at depth. The discovery of methane and carbon dioxide alongside water is crucial. These are exactly the chemicals that, in the right balance, could point to biological activity, especially in an ocean world. The unconfirmed hint of DMS adds a layer of profound possibility. Could life exist in such a place, not on the surface, but in the dark, pressurized depths of a global ocean, drawing energy from chemical gradients or the planet's internal heat? K218b represents a paradigm shift. It tells us that the search for life cannot be limited to Earth-sized, rocky planets. Entire categories of worlds we once dismissed as gas-shrouded infernos may, in fact, be the most common abodes for life in the galaxy. If a Hycean world can host the chemistry we associate with biology, then the cosmic ocean of possibilities has just grown exponentially deeper. The implications of a Hycean world are nothing short of revolutionary for our search. For decades, the gold standard was finding an Earth twin, a rocky planet with a thin, nitrogen-oxygen atmosphere in the habitable zone. But K218b and the Hycean hypothesis force us to ask a different question. What if the most common cradle for life in the cosmos is not a familiar shore, but a planet-wide, superheated sea under a crushing sky of hydrogen? This changes everything about where we look and what we look for. A thick hydrogen atmosphere is not a death sentence. It could be a planetary life support system of incredible durability. On a planet orbiting far from its dim star, where sunlight is weak, that deep hydrogen blanket acts as a supremely efficient greenhouse. It traps what little stellar heat there is, preventing the world from becoming a frozen snowball and instead maintaining a vast, global liquid ocean, even in the cold outer reaches of a star's influence. Conversely, for a planet huddled close to a turbulent red dwarf, that same atmosphere becomes a formidable shield. It can deflect and absorb the punishing stellar flares and ultraviolet radiation that would sterilize a world like Earth, protecting any ocean beneath. In both scenarios, the result is the same: a stable, global aquatic environment that could persist for billions of years. Stability is the key ingredient life needs to experiment to begin. And within the dark, pressurized depths of a Hycean ocean, away from a violent surface, conditions might be surprisingly gentle. The water temperature could be warm, even comfortable, sustained by the planet's internal heat or the insulating atmosphere. Here, in eternal darkness, life would not rely on sunlight, but on chemistry. Hydrothermal vents on the seafloor, like those in Earth's deepest oceans, could provide the energy and mineral richness for microbes to thrive. The entire planet becomes a single, interconnected biosphere, a dark water world teeming with potential. This means our telescopes must now scan a much wider array of planets. Mini-Neptunes, once ignored, become prime targets. The James Webb Space Telescope is perfectly suited for this new hunt. It can analyze the atmospheres of these larger, gas-shrouded worlds with greater ease than the thin air of rocky planets, searching for the telltale cocktail of gases, water vapor, methane, and carbon dioxide that might hint at a living ocean below. The discovery of a single Hycean world with strong biosignatures would prove that life is not a delicate accident limited to Earth-like conditions, but a robust, creative force that can take root in the most alien of seas. It would suggest that the galaxy, filled with these common worlds, might be far more lived in than we ever dared to dream. Yet even a world with a global ocean needs a stable, gentle sun to nurture it. 100 light-years away, we find a star that offers exactly that, and a planet that has become a new standard for hope. In the quiet constellation of Dorado, the Transiting Exoplanet Survey Satellite, or TESS, made a landmark discovery. It found TOI 700d, the first Earth-sized planet in the habitable zone ever detected by this pioneering mission. This is not a super-Earth or a mini-Neptune. With a size just over 20% larger than our own world, TOI 700d is a true rocky sibling, orbiting a calm M-dwarf star. This star, TOI 700, is a model of stellar tranquility. Unlike the flare-prone red dwarfs that threaten their planets, this star is exceptionally quiet, with no significant flare activity observed. It provides a steady, dim light, creating an environment where a fragile atmosphere could persist for billions of years without being stripped away. The planet itself completes a leisurely orbit every 37 days, a year spent entirely within the star's temperate habitable zone. But what kind of world awaits under that steady crimson glow? Scientists have run complex climate models to explore the possibilities, and the results paint two equally compelling portraits. One scenario suggests TOI 700d could be a water world, its surface almost entirely covered by a deep global ocean, with perhaps only a chain of volcanic islands breaking the endless water. The other major model points to a very different reality, a world with a significant landmass but shrouded under a thick, global layer of clouds. These clouds would reflect much of the star's already faint light back into space, creating a cooler, more stable climate. From space, this planet would appear as a featureless, bright white marble, hiding all its secrets beneath that perpetual overcast. This duality makes it a fascinating puzzle. Is it an ocean planet or a cloud-shrouded continent? The answer lies in its atmosphere, and that is why TOI 700d has become a premier benchmark for the next generation of astronomy. Its combination of factors is a gift to scientists. It transits its star regularly from our viewpoint. It orbits a quiet and bright star, and it is the right size and temperature to be profoundly interesting. This makes it one of the most favorable targets in the sky for the James Webb Space Telescope. Webb will soon begin analyzing the starlight that filters through TOI 700d's atmosphere during each transit, hunting for the chemical fingerprints that will tell us which model is correct. Detecting water vapor would point strongly toward the ocean world hypothesis. Finding certain aerosols or a specific atmospheric composition could confirm the global cloud deck. This world is more than just another candidate. It is a key. It represents our best chance to move from theoretical models to concrete data about the climate of an Earth-sized world in another star's habitable zone. What we learn here will calibrate our entire search, teaching us how to interpret the signals from other, fainter planets, and bringing us one definitive step closer to understanding what it truly takes for a small, rocky world to become a living one. Buried in the vast archives of data from the Kepler telescope, a second look revealed a hidden gem. Kepler 1649c was not found in the initial sweep, but by scientists and citizen scientists painstakingly reanalyzing old observations. Their perseverance paid off with a stunning discovery, the most Earth-like exoplanet in size and temperature ever found by the Kepler mission. This world is a near-perfect match in two critical ways. First, its size is almost identical to ours, measuring just 1.06 times the radius of Earth. Second, and perhaps more remarkably, the amount of starlight it receives from its red dwarf sun is calculated to be about 75% of the sunlight Earth gets from our own star. This places it firmly in the habitable zone with an energy budget strikingly similar to our own planets. On paper, Kepler 1649c is the closest thing to an Earth twin we have found in terms of these fundamental, life-enabling parameters. It feels like a revelation pulled from a forgotten file, a world that was there all along, waiting for a closer look. Yet, as with so many promising red dwarf planets, this similarity comes with a profound asterisk. Kepler 1649c orbits extremely close to its dim star, completing a year in just 19.5 Earth days. This almost certainly means it is tidally locked, with one hemisphere in permanent daylight and the other in endless night. The central question of its habitability hinges entirely on whether it can overcome this stark division. Could an atmosphere thick enough to exist on such a world circulate heat from the blazing day side to the frozen night side, creating a temperate band in between? Or would the atmosphere itself freeze out on the dark side, collapsing the entire system into a world of extremes? The potential climates are a subject of intense modeling. Some simulations suggest that with a substantial Earth-like atmosphere, global circulation could indeed prevent atmospheric collapse, potentially creating habitable conditions across much of the planet, especially along the Terminator line. Other models are less optimistic, pointing to the challenges of maintaining liquid water. What makes Kepler 1649c so compelling, however, is its baseline. We are not starting with a super-Earth or a mini-Neptune and imagining it could be Earth-like. We are starting with a world that is, in its most basic physical properties, virtually Earth's sibling. This gives our climate models a much more familiar starting point, making the predictions for its potential environments more robust. It represents a different kind of hope, not for the strangest or most exotic life, but for the possibility of something recognizably akin to our own planet's conditions, albeit under an unmoving sun. This rediscovered world stands as a testament to the treasures still hiding in our data, and a reminder that our best cosmic twin might have been quietly waiting in the shadows all along. 31 light-years away, a world exists that defies our simplest assumptions about where life could survive. Discovered by the transiting exoplanet survey satellite, GJ357d is a super-Earth with a staggering mass at least 6 times greater than our own planet. It orbits a quiet M-dwarf star, a dim red sun, and completes a full year in just 55.7 Earth days. Its location is firmly within the star's habitable zone, but the sunlight that reaches this distant world is feeble, far weaker than what Mars receives from our Sun. At first glance, this seems like a disqualifying detail. How could a world receiving less stellar energy than the frozen, arid Mars possibly host liquid water? The answer lies not in the light from above, but in the potential blanket wrapped around the planet itself. The key to GJ357d's habitability is a thick, dense atmosphere, and not just any atmosphere. Climate models point to one specific gas as the planet's potential savior: carbon dioxide. If this super-Earth possesses a sufficiently thick envelope of CO2, something remarkable could happen. Carbon dioxide is a powerful greenhouse gas. On Earth, in modest amounts, it helps keep our planet warm. But on a world like GJ357d, a much denser CO2 atmosphere would act like an immense global thermal blanket. It would trap every bit of the star's faint heat with incredible efficiency, preventing it from escaping back into space. This runaway greenhouse effect, so dangerous on a world like Venus, could here be the very engine that creates a temperate climate. The models suggest that with the right atmospheric pressure and composition, the surface of GJ357d could be warmed to the point where liquid water not only exists, but flows freely. It is a profound lesson in planetary science. A world's surface temperature is not dictated by starlight alone. It is a delicate balance between the energy coming in and the atmosphere's ability to retain it. GJ357d shows us that the outer edges of a star's habitable zone are not necessarily cold deserts. They can be worlds swaddled in their own heat, where a dense, insulating shroud makes up for the dimness of their sun. The possibility that it is a rocky world only adds to the intrigue. With its immense mass, it likely has a solid surface, perhaps with towering mountains and deep valleys, all under a perpetual, hazy orange sky pressurized by that thick air. Its relative proximity to Earth makes it a tantalizing target for the next generation of telescopes, a nearby laboratory to test whether a planet can truly warm itself into habitability against all odds. The quest for a true Earth analog brings us to a pair of worlds discovered by the Kepler telescope. Two of the most Earth-like exoplanets we have ever identified by the numbers. Kepler 438b and Kepler 442b orbit different stars, but together they represent a tantalizing step toward finding a planet that mirrors our own. In terms of sheer physical similarity, they are extraordinary. Both are rocky super-Earths, only slightly larger than our planet. More importantly, the amount of starlight they receive, what scientists call stellar flux, places them squarely in the habitable zones of their respective suns. Kepler 438b receives about 40% more light than Earth gets from our Sun, suggesting a climate that could be warmer, perhaps subtropical across much of its surface. Kepler 442b, on the other hand, receives about 70% of Earth's light, hinting at a cooler, more temperate global environment. On paper, these are the closest matches we have found, worlds where the sunlight itself feels almost familiar. Yet the stars they orbit tell two very different stories, and it is here that their paths diverge dramatically. Kepler 438b circles a highly active red dwarf star, one prone to violent and frequent superflares. These eruptions of radiation are hundreds of times more powerful than anything our Sun produces, and they could be catastrophic for a nearby planet's atmosphere. Even if Kepler 438b began with a thick, protective blanket of air, its star may have eroded it away over billions of years, leaving the surface exposed to harsh ultraviolet radiation and stellar winds. This stellar violence casts a shadow over its Earth-like credentials, a reminder that a perfect orbit means little if the local sun is a constant threat. Kepler 442b, however, orbits a much quieter, more stable star. While still a red dwarf, it shows far less flare activity. This calm stellar environment is a gift of time and stability. It means that if this planet formed with an atmosphere and oceans, it has likely been able to hold on to them, allowing conditions to remain constant over geologic epochs. That stability is the single most precious commodity for the emergence of life. So while Kepler 438b might look better on a spreadsheet with its slightly warmer, sunnier position, Kepler 442b, with its cooler light and peaceful star, emerges as the far more promising candidate for a living world. It is a powerful lesson in our search, a reminder that we must judge a planet not just by its own characteristics, but by the temperament of the sun it calls home. The quieter star may well nurture the louder possibilities. A quiet revolution is unfolding in our cosmic backyard. In the year 2023, astronomers made an announcement that sent ripples through the world of exoplanet science. Just 31 light-years away, orbiting a dim red dwarf star named Wolf 1069, they found a world that defies the odds. This planet, Wolf 1069b, is not a super-Earth or a mini-Neptune. It is a true rarity, a planet with a mass almost identical to our own Earth, and it sits perfectly within its star's habitable zone. In the grand catalogue of thousands of exoplanets, worlds that match Earth in both size and temperature are vanishingly few. This makes Wolf 1069b a precious benchmark, a nearby laboratory for understanding what it truly means to be an Earth-like world. Like many planets orbiting calm red dwarfs, it is almost certainly tidally locked. One face forever bathes in the dull red light of its sun, while the other is plunged into eternal night. This stark division would seem to create two hostile extremes. Yet sophisticated climate models reveal a surprising possibility. If Wolf 1069b possesses an atmosphere similar to Earth's in composition and pressure, something remarkable could happen. The atmospheric circulation could act as a powerful planetary heating system. Winds would carry warmth from the scorching day side across the terminator line, distributing it far into the night hemisphere. This process could prevent the atmosphere from freezing out entirely on the dark side. The result: vast regions on the planet's permanent day side, not just a narrow sliver, could maintain temperatures above freezing. In these sunlit lands under that unmoving crimson sun, liquid water could pool in lakes, flow in rivers, and perhaps even fill shallow seas. The models suggest that with a robust atmosphere, over half of the planet's day side could be temperate, a sprawling landscape of potential habitability. This transforms our view of tidally locked worlds from hostile prisons into potential havens. Because of its proximity and its ideal characteristics, Wolf 1069b has instantly become a crown jewel for future exploration. It is a prime target for the next generation of giant telescopes, like the extremely large telescope being built in Chile. These instruments will not just study its atmosphere indirectly, they will attempt the monumental task of direct imaging. The goal is to capture its actual light, a faint speck separated from the glare of its star, and analyze that light to map its surface temperatures and perhaps even detect continents and oceans. This world is more than a data point. It is a promise of a future where we might one day see the first pixelated image of another potentially living planet. That promise of a temperate world under a red sun is one vision of habitability, but a different star offers a more familiar rhythm. 42 light-years away in the constellation Pictor, orbits a planet that first sparked the imagination of a generation of exoplanet hunters. HD 40307G is a super-Earth, a world with a mass at least 7 times greater than our own. It circles a star slightly cooler and smaller than our Sun, a quiet orange K-type star, completing a leisurely orbit once every 200 days. This places it squarely within the star's habitable zone, a world with a year length reminiscent of our own, but with a gravity that would feel profoundly different underfoot. The fundamental mystery of this planet is its very nature. Is it a colossal rocky world, a super-sized version of Earth with vast continents and deep metal cores? Or is it a mini Neptune, a world with a small rocky heart but swaddled in a thick, gaseous shroud of hydrogen and helium? We simply do not yet know. This ambiguity makes it a fascinating archetype. If it is a massive rocky planet, its surface could be a geologist's dream, with towering mountain ranges and tectonic activity on a scale we cannot imagine, all under an orange-tinted sky. Its stronger gravity would pull its atmosphere closer to the surface, potentially creating denser air and profound pressure differences. But there is another clue that adds to its intrigue. The planet's orbit may not be a perfect circle. It might be slightly elliptical, meaning its distance from its star changes over the course of its 200-day year. This small variation could be the key to a dynamic world. If true, HD 40307G could experience distinct seasons, not caused by a tilted axis like Earth, but by its changing proximity to its Sun. Imagine a year where the planet swings closer, experiencing a warmer summer, before retreating to a cooler, more distant winter. This cyclical rhythm of temperature and climate could drive complex weather patterns and ocean currents, creating a world of rich environmental diversity. For astronomers, this planet holds a special historical place. When it was confirmed in 2012, it was one of the very first worlds ever identified within the habitable zone of a star similar to our Sun. It represented a turning point, proof that the sweet spot for life was not exclusive to our solar system or to violent red dwarfs. It opened the door to the idea that stars like our own could host their own families of temperate worlds. While newer discoveries have refined our search, HD 40307G remains a foundational candidate, a reminder of the early excitement in the hunt and the enduring mystery of what kind of world truly lies in that gentle orange light. Just 11 light-years from Earth, a world orbits in profound silence. Ross 128b circles one of the quietest red dwarf stars ever discovered, a stellar neighbor so calm it has shown no signs of the violent flares that plague so many of its kind. This tranquility is its greatest gift. While Proxima Centauri b endures a tempestuous relationship with its star, Ross 128b exists in a state of remarkable peace. Its star provides a steady, dim light, an unwavering beacon that has likely shone gently for billions of years. For a planet, this means stability on a timescale that life could use. Without constant stellar eruptions tearing at its atmosphere, Ross 128b has a far better chance of holding onto a protective blanket of air, a crucial shield and climate regulator. The planet itself is a super-Earth with about 1.35 times the mass of our world, suggesting a solid, rocky surface. Its orbit of just under 10 days places it snugly within the habitable zone, and climate models indicate that with a reasonably Earth-like atmosphere, its surface temperatures could be remarkably mild, potentially even similar to Earth's global average. This combination of factors, a quiet star, an Earth-like mass, and a temperate orbit, makes it one of the most compelling and serene candidates in our entire catalog. It represents a different path for red dwarf planets, not one of survival against a star's fury, but of potential nurturing under a constant, gentle glow. If life requires a long, uninterrupted period of stable conditions to emerge and evolve, then Ross 128b offers a sanctuary that worlds like Proxima Centauri b can only dream of. It is a reminder that in the cosmic search for a home, sometimes the most promising places are not the most dramatic, but the most steadfast. Kepler 22b was a revelation that arrived like a burst of light in a dark room. Announced in 2011, it was the very first planet discovered by the Kepler telescope to orbit comfortably within the habitable zone of a Sun-like star. The announcement carried an electric sense of possibility, a feeling that we had finally found a world that could mirror our own. Here was a planet orbiting a star very similar to our Sun, in the region where liquid water could exist. The initial excitement was palpable, a milestone that seemed to mark the beginning of a new era. Yet, as we looked closer, Kepler 22b taught us our first profound lesson in cosmic humility. Its size, about 2.4 times the radius of Earth, placed it in a mysterious category. It was too large to be a simple rocky planet like our own, but perhaps too small to be a full gas giant. This planet could be one of two radically different things. It might be a super-Earth, a massive rocky world with a solid surface, perhaps shrouded in a thick, steamy atmosphere. Or it could be a mini-Neptune, a world with a small rocky core enveloped by a deep, gaseous hydrogen and helium atmosphere. An ocean world of a very different and likely uninhabitable kind. We simply could not tell from the data we had. This ambiguity was its greatest gift to science. Kepler 22b forced astronomers to confront a crucial truth. Finding a planet in the habitable zone is not the end of the search. It is merely the opening chapter. Orbit and temperature are just the first, simplest clues. The real story of a world is written in its composition, its atmosphere, and the temperament of its star. This pioneering discovery shifted the entire conversation. It moved us from simply counting planets in the zone to asking much deeper, more complex questions. What is this world actually made of? Does it have a surface on which water could pool? Or is it all crushing gas and ice? Could it hold an atmosphere long enough for chemistry to become biology? Kepler 22b, that first beacon of hope, became the puzzle that defined the modern hunt. It showed us that the path to finding another Earth would be filled with fascinating, ambiguous worlds that challenge our definitions and expand our imagination, reminding us that the universe is under no obligation to build planets to our specifications. This ambiguity between a super-Earth and a gas world brings us to a planet that embodies that mystery perfectly. GJ1214b is a world that defies our solar system's simple categories. Discovered orbiting a dim red dwarf star 48 light-years away, it is classified as a mini-Neptune, a type of planet completely absent from our own neighborhood. It is about 2.7 times the size of Earth, but nearly 7 times as massive, telling us it is not a solid ball of rock. Instead, it is a world swaddled in an immense, deep atmosphere, a shroud of gas hundreds of miles thick. This planet orbits so close to its star that its year is a blistering 38 hours long, and its surface temperature is estimated to be a scorching 500 degrees Fahrenheit. For surface life as we know it, this is an inferno. Yet, GJ1214b is not a dead end in our search for life, but a window into a far more common cosmic reality. Planets of this size and type, these mini-Neptunes and sub-Neptunes, are among the most abundant in the Milky Way galaxy. To understand the potential for life in the universe, we must first understand them. GJ1214b has become a premier laboratory for decoding the secrets of these steamy, shrouded worlds. When astronomers point their telescopes at it, they are not looking for a surface, but trying to peer down through the top layers of its immense atmosphere. The data presents two equally fascinating possibilities. One is that its atmosphere is dominated by water vapor, a superheated, steamy envelope so thick and dense that it creates a permanent global pressure cooker. The other leading theory is that the planet is blanketed by a uniform layer of high-altitude clouds or haze, perhaps made of salts or other compounds, which completely obscures our view of the deeper atmospheric layers. Both scenarios are profoundly alien. A water-world atmosphere would mean that beneath the clouds, conditions could transition from vapor to a bizarre, hot fluid water ocean under crushing pressure, a possible cousin to the Hycean worlds. A global cloud deck, on the other hand, shows how some planets can develop a permanent, featureless shield. By studying how starlight filters through this world's alien air, scientists are learning the basic physics and chemistry of the most common type of planet in our galaxy. GJ1214b teaches us that to find life, we must first master the language of the clouds and vapors that cloak the most ordinary of worlds. That enduring search for stability leads us to a star that offers a gentler rhythm than the flaring red dwarfs. Orbiting the orange K star HD 85512, about 36 light-years away, is a super-Earth named HD 85512b. This world is substantial, with a mass estimated at 3.6 times that of our own planet, suggesting a rocky surface under a stronger gravitational pull. Its orbit is tight and fast, a year that races by in just 54 Earth days, placing it at the very inner edge, the warmer boundary of its star's habitable zone. At first glance, this proximity might seem to doom it to a runaway greenhouse effect, a fate like Venus, but sophisticated climate models reveal a delicate and fascinating balance. The key to this world's potential habitability could be something as simple and as complex as clouds. Researchers have calculated that if HD 85512b possesses an Earth-like atmosphere and a surface covered by at least 50% cloud cover, something remarkable happens. Those clouds, reflecting a significant portion of the incoming stellar energy back into space, would act as a global sunshade. This natural planetary thermostat could cool the surface just enough to prevent the oceans from boiling away, potentially maintaining global average temperatures that allow for liquid water. It is a world where the sky itself holds the secret to its stability. The significance of HD 85512b extends beyond its clever climate. Its star is a quieter, more mature K-type star, far more stable than the turbulent red dwarfs that host so many of our candidates. This stellar calm provides a potentially longer, quieter window for life's experiments. Without the constant threat of apocalyptic flares, an atmosphere can persist, and chemical processes can proceed undisturbed for billions of years. It represents a different class of opportunity, a planet that trades the extreme tidal locking of red dwarf worlds for a rapid orbit around a steadier, warmer sun. Here, the challenges for life are not stellar violence or eternal darkness, but mastering the art of global climate control through its own skies. 12 light-years from Earth shines a star that feels almost familiar. Tau Ceti is a G-type star, a yellow sun very much like our own, a stellar sibling in our galactic neighborhood. Orbiting this sun-like star is a world that presents a stark warning about the fine line between paradise and inferno. Tau Ceti e is a super-Earth, a planet with a mass at least 4 times that of our own, and it orbits perilously close to the inner edge of its star's habitable zone. The sunlight bathing this world is intense, far stronger than what Earth receives. This position makes it a prime candidate for a terrifying fate, that of a super-Venus. Imagine a world where a runaway greenhouse effect took hold early in its history. The intense solar energy could have boiled away any initial oceans, filling the atmosphere with colossal amounts of water vapor, a powerful greenhouse gas itself. This would have triggered a catastrophic feedback loop, driving surface temperatures to hundreds of degrees, hot enough to melt lead. The atmosphere could have become a thick, toxic soup of carbon dioxide and sulfuric acid clouds, with surface pressures crushing anything that might have once lived. Tau Ceti e serves as a cosmic cautionary tale, a reminder that simply being in the habitable zone does not guarantee a habitable world. It shows us the warmer boundary of possibility, where a planet's climate can tip over into a permanent global oven. Yet, in the same system, a very different story unfolds farther out. Its sibling, Tau Ceti f, orbits in the colder, outer reaches of the star's habitable zone. This super-Earth takes nearly 600 days to complete a year, receiving only a fraction of the stellar energy that reaches Earth. Here, the danger is not heat, but deep, global cold. Without a thick, insulating atmosphere rich in greenhouse gases, Tau Ceti f would be a frozen snowball, a world locked under miles of ice. But if it possesses that crucial atmospheric blanket, it could maintain liquid water, perhaps as a global ocean beneath an icy crust or in temperate regions. These two worlds, E and F, represent the extreme bookends of their sun's habitable zone, one a potential hellscape, the other a potential icebox, but both face a shared, violent challenge that makes this entire system a perilous place for life. Observations reveal that Tau Ceti is surrounded by a massive debris disk, a sprawling belt of asteroids, comets, and dust far denser than the one in our own solar system. This means the planets here are likely subject to a constant, heavy bombardment from space, impacts far more frequent and devastating than what Earth experiences. For any fragile biosphere trying to gain a foothold on Tau Ceti E or F, this would be an existential threat. A large impact could sterilize a planet, boiling away oceans and blanketing the sky in dust for centuries. It raises a profound question about the stability needed for life. Can biology ever get started or reach complexity in a stellar system that is still so violently unsettled? The Tau Ceti system, with its familiar sun and its two contrasting, battered worlds, teaches us that a quiet neighborhood might be just as important as the right address. The discovery of Kepler 186f was a moment that changed the scale of the search forever. Announced in 2014, it was not the first planet found in a habitable zone, nor the most Earth-like in temperature. Its monumental achievement was one of pure, simple size. Kepler 186f was the first planet ever confirmed to be roughly Earth-sized and orbiting within the habitable zone of a distant star. Before this, the worlds we found in those temperate bands were all super-Earths or gas giants, planets fundamentally different from our own. Kepler 186f proved that small, rocky worlds, built to our own blueprint, could also find that sweet spot around other suns. It orbits a cool, dim M-dwarf star about 500 light-years away, completing a leisurely orbit once every 130 days. That orbit places it at the cooler, outer fringe of its star's habitable zone, a position in its system roughly analogous to somewhere between the orbits of Earth and Mars in our own solar system. The sunlight it receives is only about 1/3 of the energy Earth gets from our sun, a faint and crimson glow. This means that for liquid water to exist on its surface, the planet would likely need a helping hand from its own atmosphere. A thick envelope rich in greenhouse gases like carbon dioxide could trap that meager starlight efficiently, warming the surface to temperate levels. Without such a blanket, it could be a frozen, Mars-like world. Its size, however, is the key detail that ignited imaginations. Kepler 186f is only about 10% larger than Earth in radius. This small difference makes it far more likely to be a rocky planet with a solid surface, rather than a gaseous mini-Neptune. We can realistically picture standing on it, looking up at a large, dark red sun fixed in a twilight sky. The symbolic power of this discovery cannot be overstated. For centuries, we wondered if Earth was a unique cosmic accident. Kepler 186f provided a definitive, data-driven answer. No, we are not alone in type. Planets built like our own, positioned where the chemistry of life is possible, are out there. It transformed the question from, do other Earths exist? To, how many are there and what are they like? This single, small world, glimpsed as a periodic dimming of starlight half a universe away, became a beacon. It proved the galaxy could indeed hold cousins to our pale blue dot, waiting in the quiet, red-lit edges of countless alien suns. Two worlds share a home under a pair of dim red suns. In the Kepler 296 system, 5 planets orbit a binary pair of M-dwarf stars, a compact family bound by a complex gravitational dance. Among them, 2 Earth-sized worlds, Kepler 296e and Kepler 296f, offer a fascinating study in subtle differences. They are built from the same stellar material, circling the same twin stars, yet their experiences of light and warmth are mirrored opposites. Kepler 296e, the inner of the pair, receives slightly more stellar flux than Earth gets from our own Sun. Its position suggests a world that could be a few degrees warmer on average than our own, a potentially subtropical planet under a crimson sky. Its sibling, Kepler 296f, orbits a bit farther out. It receives just a little less sunlight than Earth, hinting at a slightly cooler, more temperate global climate. On paper, these seem like remarkably balanced conditions, 2 variations on an Earth-like theme. But the reality of living in this system would be profoundly alien, dictated by the dual nature of their suns and a fundamental planetary condition. Both worlds are almost certainly tidally locked to their stellar hosts. One hemisphere of each planet forever faces the binary stars, basking in their combined, dull red light. The opposite side is condemned to an eternal, frozen night. This creates a planetary landscape of brutal extremes. The permanent day side would be scorched by relentless, though faint, starlight, while the night side would plunge into deep, cryogenic cold where any atmosphere might freeze solid and fall as snow. The hope for life, then, is not found on either of these vast, inhospitable halves. It clings to the razor-thin boundary between them, the Terminator line. In this narrow band of perpetual sunrise or sunset, temperatures could theoretically moderate enough for liquid water to exist. Here, under a sky where the twin red suns hang forever on the horizon, a sliver of a world could host rivers, lakes, and perhaps even simple ecosystems. The climate of this twilight strip would be governed by powerful, planet-spanning winds, as the atmosphere desperately tries to redistribute heat from the blazing day to the frozen night. Furthermore, the binary nature of the stars adds another layer of complexity. The gravitational interplay between the two stars, while likely stable, could introduce long-term cycles in the planet's orbits, potentially causing subtle shifts in the amount of light they receive over millennia. This could turn their narrow habitable bands into moving targets, expanding and contracting over cosmic timescales. Kepler 296, E and F show us that even with nearly perfect Earth-like energy budgets, a planet's story is written by its rotation and its stars. They present a vision of habitability that is not global but linear. a desperate clinging to the edge of light in a universe of stark contrasts. Yet even as we dream of distant oceans, the most accessible alien sea might be hiding in plain sight, right next door. Our journey returns to the very beginning, to Proxima Centauri. While Proxima b captured the world's attention as the first potentially habitable neighbor, astronomers discovered a second, smaller world sharing that turbulent household. This is Proxima Centauri d, a planet of profound extremes. Its mass is astonishingly small, a mere quarter of Earth's, making it one of the lightest exoplanets ever detected around a sun-like star. It whips around its dim red sun in a breakneck 5-day orbit, hugging the star so closely that its year is a fleeting blur. This proximity places it far inside what we would consider the traditional habitable zone, likely far too hot for liquid water on the surface under a normal sun. But Proxima Centauri is not a normal sun, and this tiny world presents a puzzle that challenges our assumptions about where life could cling to existence. The first and most obvious question is one of survival. Can a planet so small, so lightweight, possibly hold onto any atmosphere at all under the relentless barrage of its star's violent flares? With such low gravity, the stellar winds screaming from Proxima could have stripped away any primordial gaseous envelope billions of years ago, leaving behind a bare, scorched rock. If that is the case, Proxima d would be a barren, airless world, a silent testament to stellar fury. But there is another, far more intriguing possibility. What if this tiny world formed with an extraordinary gift, a vast reservoir of water? Imagine a planet that is not mostly rock, but a cosmic snowball, a world rich in ice and water. In the searing heat of its close orbit, that ice would have melted long ago, creating not surface lakes, but a planet-wide global ocean. This is where the story turns fascinating. A deep, global ocean could be the key to this world's enduring mystery. Water itself, under immense pressure, can act as a shield. A planet spanning ocean dozens or even hundreds of miles deep would provide a formidable buffer against the radiation from above. Life, if it ever began here, would not exist on a surface bathed in deadly ultraviolet light. Instead, it would retreat into the depths. In the eternal darkness of the subsurface ocean, protected by miles of water, conditions could be stable and temperate. The energy for life would not come from the angry red sun, but from within, from the planet's own hot core or from chemical reactions at the rocky seafloor. This vision transforms Proxima d from a scorched pebble into a potential water world, a hidden abyss. It becomes an analog for the icy moons in our own solar system, like Jupiter's Europa or Saturn's Enceladus, but on a planetary scale. Those moons are frozen on the outside, with hidden oceans warmed by gravitational squeezing from their giant planets. Proxima d could be the opposite, a world kept liquid by the external heat of its star, but with a biosphere that survives by diving deep beneath the heat to find its safe zone. It is a reminder that habitability is not a single condition, but a gradient, a set of layers. A world can be inhospitable at its surface, yet teeming with possibility just beneath. Proxima Centauri d, this tiny, swift neighbor, forces us to consider that the most promising real estate for life might not be the surface of an Earth-like planet at all, but the lightless, pressurized depths of a forgotten ocean, orbiting a star we have watched our entire lives. The architecture of the TRAPPIST-1 system offers a gift beyond its 7 worlds. It provides a laboratory where we can compare planets side by side, siblings born from the same stellar nursery, but evolving under slightly different conditions. One of the most revealing experiments in this cosmic family is the 6th planet from the star, TRAPPIST-1g. This world is a rocky planet, nearly identical in size to Earth. Yet its experience of light and warmth is profoundly different. Orbiting farther out than its temperate sibling TRAPPIST-1e, this planet receives an amount of stellar energy strikingly similar to what Mars gets from our own Sun. At first, that sounds like a death sentence for surface water, a recipe for a frozen, barren desert. But the story of a planet is not written by starlight alone. It is written by the air it holds onto. Climate scientists have run the models for TRAPPIST-1G, and the results are transformative. They show that if this distant world possesses a thick, insulating atmosphere, its fate could be completely rewritten. Two specific atmospheric recipes could turn this cold Mars analog into a potentially habitable world. The first is a dense atmosphere rich in carbon dioxide, the same powerful greenhouse gas that, in sufficient quantity, could warm the faint sunlight into usefulness. The second, even more intriguing possibility is a hydrogen-dominated atmosphere. A deep shroud of hydrogen would act as a phenomenal insulator, trapping geothermal heat from the planet's interior and creating a stable, warm environment even under that dim red sun. In either scenario, the surface temperatures could rise above freezing, allowing for liquid water to flow. This makes TRAPPIST-1G a critical piece of the system's puzzle. Its position allows astronomers to conduct a controlled experiment on a scale never before possible. With the James Webb Space Telescope, we can now point at this one quiet star and analyze the atmospheres of multiple planets in turn. We can compare the thin, possibly eroded air of the inner worlds with the potentially thick, preserved blankets of the outer ones like TRAPPIST-1G. Does it have an atmosphere at all? If so, what is it made of? Finding a thick, warm envelope on this distant world would tell us that planets on the cold edges of red dwarf systems are not doomed to be ice balls. They can be wrapped in their own warmth, creating oases where the star's light is only a faint contributor. By reading the skies of all 7 siblings together, we get a masterclass in planetary evolution, a story of how atmosphere, orbit, and stellar temperament intertwine to create, or erase, the possibility for life. This constant redefinition of habitability brings us to a world that pushes the very boundaries of the concept. Over 2,500 light-years away, Kepler 443b orbits a star a little cooler than our own Sun. This super-Earth is substantial, measuring about 2.3 times the size of our planet. Its year lasts 112 days, a journey that places it at the extreme outer fringe of its star's calculated habitable zone. The sunlight that reaches this distant world is faint and feeble, only about 1/3 of the energy Earth receives. By our traditional understanding, this should be a frozen wasteland, a snowball planet locked under miles of ice. Yet, Kepler 443b forces us to consider a powerful idea: the extended habitable zone. This is not a fixed region of space, but a flexible one that depends entirely on what a planet brings to the table. The key, once again, is the atmosphere. If this world possesses a thick, hydrogen-rich envelope, that shroud of gas could act as a planetary furnace. Hydrogen is an incredibly efficient greenhouse gas. A deep atmosphere of it would trap every bit of the star's weak heat and the planet's own internal warmth, preventing it from escaping into space. This insulating blanket could raise surface temperatures by hundreds of degrees, potentially creating conditions warm enough for liquid water even in this distant, cold orbit. It is a world that could literally create its own summer through the chemistry of its own sky. But this possibility hinges on a fundamental and unresolved question about the planet's very nature. Is Kepler 443b a gaseous mini-Neptune, a world with a small rocky core buried under an immense, crushing atmosphere? If so, its surface would be a place of impossible pressures and searing heat from the greenhouse effect, with no solid ground for an ocean to pool. The alternative is just as compelling. It might be a massive, frozen super-Earth, a colossal ball of rock and ice. In this scenario, the faint starlight would leave its surface a global ice sheet, perhaps dozens of miles thick. But beneath that frozen crust, the story could change completely. The internal heat from radioactive elements in the planet's core, or gravitational squeezing from its star, could maintain a vast, global subsurface ocean, trapped between the icy shell and the rocky seafloor. This hidden sea, cut off from the dim sun above, would be a world of perpetual darkness and immense pressure, yet potentially warm and rich with the chemistry for life. So Kepler 443b presents us with two radically different visions, both born from its position on the cold frontier. It is either a steamy, pressurized gas world or a frozen snowball guarding a secret ocean. Both possibilities exist in that extended zone, a region where a planet's own construction determines its fate far more than the faint light of its star. The line between discovery and mirage can be razor-thin. 20 light-years from Earth, a star named Gliese 581 became the center of one of the most heated and hopeful controversies in exoplanet science. In the year 2010, a team of astronomers announced they had found something extraordinary, a planet they called Gliese 581g. The data suggested a world with a mass just 3 to 4 times that of Earth, orbiting squarely in the middle of its red dwarf star's habitable zone. This was not just another candidate. It was reported to be the first truly Earth-mass world ever found in that temperate sweet spot, a potential watershed moment. The planet was quickly nicknamed Zarmina's World, after the lead astronomer's daughter, and the name captured the public imagination. Headlines declared the discovery of the most Earth-like planet yet, a world that could have continents, oceans, and a stable climate. The excitement was palpable, a feeling that we had finally found a true cosmic cousin. But science is a process of relentless scrutiny, and the celebration was short-lived. Other research teams, analyzing the same data and conducting their own observations, could not confirm the planet's signal. The subtle wobble in the star's motion attributed to Gliese 581g, they argued, was not a clear planetary signature. It could have been an artifact of the star's own complex activity, a rhythmic pulsation or flare that mimicked a planet's gravitational tug. The astronomical community plunged into a deep and public debate. Was this a groundbreaking discovery or a statistical ghost in the machine? This controversy did more than cast doubt on a single world. It highlighted the immense technical challenge at the heart of the search. Detecting a planet as small as Earth, using the method of measuring a star's wobble, is like trying to hear a whisper in a hurricane. The signal is incredibly faint, buried in the noise of the star's own turbulent behavior. The story of Gliese 581g became a masterclass in the scientific method. Extraordinary claims require extraordinary evidence, and the process of confirmation is painstaking, slow, and often contentious. It involves independent verification, new data, and sometimes waiting for better technology. While the planet's existence remains officially unconfirmed, its legacy is undeniable. It pushed our detection limits to the edge, fueled public passion for the search, and taught a vital lesson. In the quest to find another Earth, every potential discovery is a hypothesis, a starting point for a long and careful conversation with the cosmos. Our final destination lies in the quiet reaches of the constellation Cygnus. Here, Kepler 1652b completes its silent orbit, a small, rocky world that brings our journey to a close with a powerful lesson in cosmic endurance. This planet is a testament to the sheer abundance of Earth-sized worlds, measuring just 1.1 times the radius of our own planet, and sitting comfortably within its star's habitable zone. But the star it circles is one of the smallest and coolest known to host planets, a dim ember of a red dwarf. To feel any warmth at all, Kepler 1652b must huddle extraordinarily close, completing an entire year in just 2.4 Earth days. This intimate dance comes with a profound consequence, one we have seen many times on our tour. The planet is almost certainly tidally locked. One side is a permanent landscape under a dull, fixed red sun, while the other is an eternal frozen night. This extreme arrangement presents the ultimate challenge for a world like this, a phenomenon known as atmospheric collapse. The danger is not that the atmosphere will be blown away by stellar winds, though that is possible. but that it will simply freeze solid. On the permanent night side, where no starlight ever reaches, temperatures could plunge to hundreds of degrees below zero. In such profound cold, the very gases that make up an atmosphere, like carbon dioxide, nitrogen, and oxygen, could condense directly into frost and snow. They would fall from the sky and accumulate as vast glaciers of frozen air on the dark hemisphere. If this process runs unchecked, the entire atmosphere could gradually drain away, freezing out entirely on the night side, leaving the planet a barren, airless rock with a bizarre landscape of atmospheric ice caps in the endless dark. But nature is ingenious, and our models reveal that this fate is not inevitable. Two planetary features could wage a constant war against the cold, creating a dynamic and potentially habitable environment. The first is a global ocean. If Kepler 1652b possesses a planet-wide sea, that liquid water becomes a colossal heat battery and a distribution system. Ocean currents, driven by the immense temperature difference between the day and night hemispheres, would act as planetary conveyor belts. Warm water from the sunlit side would flow into the darkness, carrying life-giving heat far into the night, preventing the oceans from freezing solid, and in turn, keeping the atmosphere above them warm enough to remain gaseous. The boundary between day and night could be a swirling, tempestuous coastlines of ice and liquid water, a place of constant, violent weather where the energy of the star is fought over by sea and sky. The second savior could be the atmosphere itself. A thick, dense blanket of air, perhaps rich in greenhouse gases, would be incredibly difficult to fully collapse. Its very mass creates pressure that raises the condensation point of gases, making it harder for them to freeze. More importantly, a substantial atmosphere would generate ferocious, planet-spanning winds. These winds would ceaselessly scour the planet, ripping heat from the day side and transporting it into the heart of the night. This atmospheric circulation could maintain a temperate zone not just on a razor's edge, but across a significant portion of the planet's day side, perhaps even allowing for liquid water and stable climates under that unmoving red sun. Kepler 1652b, in all its silent, locked simplicity, embodies the central tension of the search. It presents a world with the right size, the right orbit, and the right ingredients, yet subjected to a stress test of astronomical proportions. It asks whether the basic forces of weather and water, the same currents that shape our own world, can triumph over the profound stillness imposed by a dim star. In its silent balance between freeze and flow, it represents the fate of countless similar worlds in the galaxy, and the enduring hope that life can find a way, even on the edge of light. The very definition of a habitable world is expanding before our eyes. For decades, we focused on a narrow band of space, the Goldilocks zone, where a planet is just the right distance from its star for liquid water to pool on the surface. But our own solar system has taught us a profound lesson. Look at Europa, a moon of Jupiter, far outside the Sun's traditional habitable zone. Its surface is a frozen, cracked shell of ice. Yet beneath that ice, strong evidence points to a global ocean more voluminous than all of Earth's seas combined, kept liquid by the gravitational squeezing of Jupiter. Or Enceladus, a tiny moon of Saturn, where geysers of water vapor and organic molecules erupt from a subsurface sea into space. These are not planets basking in sunlight, but hidden, dark abysses warmed from within. This revelation shatters the old map. If life can exist in the lightless oceans of icy moons next door, then why not on distant exoplanets we have already found? That frozen super-Earth on the cold fringe of its star's influence, like Kepler 443b, might not be a barren snowball. It could be an ocean world, a cosmic Europa on a planetary scale, with a biosphere thriving in eternal darkness beneath miles of ice, completely independent of the faint sun above. This expands the search from a thin ring around a star to encompass entire planetary systems, including the moons of giant planets. Imagine a Jupiter-like world, a gas giant, orbiting peacefully within a star's habitable zone. We have found many of these. Now, picture that giant planet having a large, rocky moon, an exomoon, with its own atmosphere and liquid water on its surface, warmed by both its star and the reflected glow of its giant parent planet. Such a place could be an island of habitability in an unexpected location. The search for these exomoons is already underway, a new frontier in the hunt for living worlds. But how will we know if we have found one? We must learn to read the chemical stories written in alien air. These are called biosignatures, the atmospheric fingerprints of life. On Earth, the simultaneous presence of large amounts of oxygen and methane is a powerful signal, because these gases react and destroy each other quickly. Their persistent coexistence suggests something, namely life, is constantly replenishing them. The recent, tantalizing hint of dimethyl sulfide, or DMS, in the atmosphere of the Hycean world K218b is another example, a molecule on Earth produced almost exclusively by marine phytoplankton. The next great leap requires moving beyond detecting these chemicals in the hazy light of giant planets to seeing an Earth-like world directly. That is the audacious goal of missions now on the drawing board, like the proposed Habitable Worlds Observatory. This future telescope would be designed to block out the blinding light of a star and take a direct picture of a small, rocky planet in the habitable zone of a nearby sun. It would not be a detailed map, but a single, precious pixel of light. Yet from that one pixel, we could spread its light into a spectrum, a barcode of its atmosphere. We could search for the telltale lines of water vapor, oxygen, methane, and perhaps even the complex chemistry of pollution or artificial lights. The search is evolving from finding planets in the right place, to understanding their hidden interiors, to finally reading the messages in their skies, seeking that first, definitive whisper that says, "We are not alone." From our own stellar neighborhood to the distant edges of the Kepler field, this journey across 30 worlds has painted a new map of the cosmos. It is a map not of empty space, but of potential homes, each with its own story of fire, ice, and enduring hope. We have stood on the twilight line of tidally locked worlds, dove into the pressurized depths of global oceans, and witnessed planets swaddled in thick, life-giving atmospheres under faint red suns. The sheer diversity is staggering, yet clear patterns have emerged. Red dwarf stars, small and plentiful, host the majority of our candidates, offering both the promise of stability and the peril of stellar fury. We have learned that a planet's fate is a constant negotiation between the violence from above and the resilience from within, between the crushing grip of gravity and the delicate dance of atmospheric chemistry. Most thrillingly, our definition of a living world has exploded beyond the rocky, Earth-like planet. We now actively hunt Hycean worlds, shrouded in steam and hydrogen, and frozen super-Earths that may hide warm, dark seas. The question is no longer if such places exist, but what breathes within them. Our tools have evolved in lockstep with our imagination. We are no longer just counting planets in the habitable zone. We are now reading the stories written in their light, using observatories like the James Webb Space Telescope to decode the chemical signatures in alien air, hunting for the subtle fingerprints of water, methane, oxygen, and perhaps one day, a molecule that shouts of biology. Every night, when you look up at those pinpricks of light, remember this: you are not looking at a static backdrop. You are looking at a neighborhood, a galaxy filled with water worlds and twilight realms, with silent giants and hidden abysses. With every new telescope we build and every new world we analyze, we are not just gathering data. We are closing the distance to an answer. We are listening for a whisper across the light years. The greatest discovery in human history is waiting, and it is closer than we ever dreamed. Which of these 30 worlds captured your imagination the most? Let us know in the comments below. If you enjoyed this cosmic tour, Be sure to like this video and subscribe for more journeys to the edge of understanding. Until next time, keep looking up.